we've mentioned trend lines already. So what are trends? Well, trend lines, we think of them as lines of best fit, and they go through as much of the data as possible. We generally describe how the trend goes by using the trend line. So they are calculated using a mathematical formula that we're not going to talk about in grade 9. But a trend is generally describable as a usually rather obvious association between two or more variables. If it's not very obvious, it's usually not called a trend. Now, this relation between these two variables might be a straight line, or it might be a sine wave. Or alternatively, it could be some other shape, like a polynomial, or logarithmic, or so exponential, so on. Now, when you have a trend line, you can interpolate. What is interpolation? Well, interpolation means, look, I have a line of best fit on my data, so I can use this to approximate, hey, at this particular value for the independent variable, we should have about this value for the dependent variable. There's a little problem with this. It really works well only inside the data range. And also, your trend line, your line of best fit, or curve of best fit as the case may be, it must fit your data properly. In other words, if you accidentally use the line for data that is in fact, say, polynomial or logarithmic or so on, that might be a bit of a problem, especially if you do it over a large enough range. Now, if you extrapolate, even a linear relation has a problem. For example, mouse heart rate versus temperature of surroundings. Between 0 and 40-ish degrees Celsius, you will detect a relationship. Now, if you interpolate, that usually gives you some reasonable numbers. If you extrapolate, not so much. For example, consider 500 degrees Celsius. Yeah, this was one of the examples that was given to us in data management class for talking about why extrapolation is often very, very, very stupid. Interpolation is reliable. Extrapolation, yeah, okay, it's useful, as the case may be, to estimate a value beyond the range of a set of data, but sometimes use of brain is very important if you're going to take any extrapolated number into any calculation. A line of best fit is a straight line that comes closest to the points on a scatter plot. Technically, this closest is distance squared, but that is because of the mathematical formula used to calculate it, and is not important for grade 9. Now, a curve of best fit is what happens when instead of a linear relation, you have a nonlinear relation and you must fit a curve to it. So, it's exactly what the name suggests. The best curve you can draw through these particular points you're dealing with. A distance time graph is a common type of graph that requires, as the case may be, a line or several lines joined by curves of best fit. Now, why does a distance time graph require a line of best fit if you have, say, a radar gun and you're measuring the movement of a vehicle toward you or away from you? Well, there's always going to be some measuring error, so your data is always going to be a little bit wobbly. So clearly, this is actually a relatively smooth motion of the car away from you. It's not like the car is just doing this, moving away. Well, admittedly, I was probably shaking a little bit more there than this strictly warranted. Per se, distance versus time. But the point remains that this should really be smoother, which means that you will have lines of best fit used with the data points where you actually measured the car's distance from you. Now you'll notice that most radar guns end up giving smoother readouts because they themselves smooth out the noise, so to speak, in their detection, i.e. the random error. Now, here we see the table that we had last section. So in this table, is there a trend? Well, clearly yes. So is this a linear or nonlinear relationship? Nonlinear. And we had we remember when we plotted it last section, right? Nonlinear. With an asymptote. So an asymptote is, in theory, a value that is never reached, but infinitely approached. So for example, 1 over x has asymptotes of x equals 0 and y equals 0. Now, technically speaking, we did manage to reach it, the value where you end up flatlining, but it is reasonable to say that if you had to fit a line to this, you would end up with a curve that has an asymptote. Because, well, although over time they converge to 100, there will always be occasional slip-ups where they might dip a little below, which means that when averaged out, it is asymptotic. Now, can we make judgments on data without doing the scatter plot? Yes, because we can do a scatter plot mentally, or we can just look at the data and, oh look, there is one difference from last sections, which is this went from 80 to 78. So we look at this data and we can pretty clearly see that there is a relationship. And as the time in months increases, the increase over time, the rate of increase, slows down. Which means that it is most likely either rational or some polynomial or logarithmic or similar. Now in this case, with an asymptote, it is most likely going to be best modeled by, say, a rational function. Example 3. Hey, this is familiar too. What sort of best fit does this have? Well, this could be part of a sine wave. Because every year the temperature oscillates up and down and up and down and so on. So that cyclic, well, change might be a sine wave. Alternatively, this could be another form, like a logistic function. Now, logistical growth in biology is a term used for an S-shaped curve, which looks like, well, an S. Except, wait a second, if we have a plot of, say, a population over time, can it ever bend back on itself? Clearly not. Therefore, logistical would be like this. So from basically a lower equilibrium to a higher equilibrium. Now, what about another problem? Well, what about another type of fit? Let's see. This could be linear. Although, as I'm pretty sure we are all very aware of, given the various seasons and the cycle of temperatures, it is not linear. But it could be vaguely linear over this range. I personally think sine wave would be the best in terms of choices for best fits, but I don't think you guys have done sine waves yet. Sine waves are essentially a periodic waveform. Now, it is trigonometry related, and I'm reasonably sure in grade 9 you haven't done it yet. Now, example 3. Draw what you think a distance time graph might look like for a ball being held in place under a sonic distance sensor. And it is released to bounce off the ground. Let's say it bounces off the ground once. Alright, it's held in place under a sonic distance sensor. So we're measuring the distance from the sensor to the ball. That means that when we let go of the ball, the distance goes up, and then it comes back, and, well, the general point remains that here we see the distance increasing after we let go of the ball. This is not a sensor put on the ground measuring the distance of the ball to the sensor. This is a ball that is held under a sensor, and then eventually you let go. Upon which it begins to fall, it hits the ground, and it starts bouncing. You'll also note that here I drew the second bounce, this second highest event, as being lower, as in farther away from the sensor than the first one, where you are holding it. Why? Because balls do not bounce off the ground elastically. Elastic collisions keep all the kinetic energy as well as all the momentum, and that's not what actually happens. As you can tell from the sound of a ball hitting the ground, not all of the energy is conserved. Some of it is bled off as heat as well as sound. Alright, so that's it for this section. This section, well, for the most part, the example questions will be a judgment of how trends look and whether this should be a linear trend or a non-linear trend. Of course, it's usually pretty obvious in the sense of, oh hey guys, we have a trend that looks like this. Does this look linear or non-linear? Well, I think you guys can all figure out that this trend is not linear. Of course, what is it though? Well, we know that, say, x squared would be upward opening. But how do we move it away from, say, 0, 0 being at the bottom point to, well, here? Well, that's something we'll cover when we start talking about polynomials. So, see each other again next section then.